This video is going to cover Section 2.3 regarding polynomial functions, and it's going to cover targets 2.6, 2.8, and 2.9 that you can determine end behavior of a polynomial given its equation. You can list all the roots of a polynomial, that means x-intercepts or zeros, and then you can sketch the graph of a polynomial given its equation or its roots, and then also write the equation given its roots, and then state the domain and range. So to begin, a polynomial function of degree n is the sum of the terms where the coefficients are real numbers and the exponents are non-negative integers. And so I have two examples here. F of x equals 3x to the fifth minus 4x to the fourth plus 6x cubed plus 12x squared minus 10x plus 9. This is a polynomial. You'll see that there's different terms being added or subtracted together. All the coefficients, the numbers in front of your x's, are real numbers, and then all the exponents are non-negative integers, so they are 0. That's where 9 comes in. That would be x to the 0 power, or they're greater than that. They're positive. There's two different ways to write a polynomial function. This first form that I have is called standard form. This is where you have the largest exponent first, and then it's written in descending order. And then the other way to write a polynomial is called the product of its factors. And so this is just another way of writing a polynomial. This is really helpful if you know the roots or the x-intercepts. Polynomial functions are classified by their degree, and this is always the largest exponent. The degree tells you the number of roots a polynomial has, both real and imaginary. Roots are also called zeros or x-intercepts. The only thing is, when it comes to the imaginary roots, don't call them x-intercepts, always call them imaginary roots. So we'll probably be using the word root from now on instead of x-intercepts. So for example, that 3x to the fifth polynomial that I had written on the first slide is a fifth degree polynomial because that's what the largest exponent is. The other way that we had it written was in the product of its factors, and this doesn't tell you yet what its degree is. You have to add the exponents. So this would be to the third power, and then this would be to the first. So this would tell me that this is going to be a fourth degree polynomial. Graphs of polynomials. The basic properties are, first of all, that the graph is continuous. It can be drawn without lifting up the pencil. The second property is that it has smooth curves and there are no sharp turns, so not like an absolute value would be a good example of what a polynomial is not. It has to have smooth curves. Relative maximums and relative minimums. We talked about this in chapter 1. So like on this drawing that I have here of a polynomial, there's a relative maximum up here and a relative minimum down here, even though the graph goes on forever. But those would be considered relative because that's where the graph changes from increasing to decreasing and decreasing to increasing. And then the last thing is that all polynomials have x-intercepts or roots. The end behavior. This is what happens on the ends of a polynomial, and we do something called the leading coefficient test. The leading coefficient is always the number in front of the highest power. So if we have an nth degree, so x to the n power, that a sub n, that just means the number in front of the largest exponent. So you don't really have to worry about this notation here. So for example, what is the leading coefficient of f of x equals negative 3x to the fourth plus 5x squared minus x plus 1? This would be a negative 3. That's the number in front of the largest exponent. What about the leading coefficient of 9x plus 2x to the fourth plus 6x to the fifth plus 3? Now you'll notice this is not in standard form. It's not the largest exponent and then in descending order. My leading coefficient would be a positive 6 because that's in front of the largest exponent. So end behavior, there are two things that you want to look at. The first thing is that the largest exponent is odd. If your largest exponent is odd and then you have a positive leading coefficient, your graph will look something like this. Now don't worry about what's going on in the middle. We're only concerned right now about what the end behavior is. So we would say that a polynomial that has an odd degree and that the leading coefficient is positive, it would fall to the left and it would rise to the right. Or you could say down, left, up, right, or falls and rises, whichever you prefer. Then if we had a negative leading coefficient, my graph would be a little bit different. Remember, it doesn't matter what's going on in the middle. If you have a leading coefficient that's negative with an odd degree, so to the third or to the seventh, to the fifth, to the ninth, my graph, it's going to rise to the left and fall to the right. So remember, a negative leading coefficient flips a graph. And so that's why the end behavior changes from direction to direction. The next part is if you have your largest exponent is even. So if you have an even degree, and then you have a positive leading coefficient, so what does the end behavior do? So remember, it doesn't matter what's going on in the middle. This can apply to a parabola, it could apply to a fourth degree, a sixth degree. If it's an even degree and it's positive, it's going to rise left and rise right. But then if you have a negative leading coefficient and an even degree, the end behavior is that it's going to fall left and fall right. So for these examples, I just want you to state whether the degree is even or odd, whether the leading coefficient is positive or negative, and then determine the end behavior. So for this first example, look at the degree, look at the largest exponent. So it's going to be an odd degree, and then the leading coefficient is negative, and so then that means it's going to rise left and fall right. In number 2, my leading coefficient is, my degree is 8, so it's an even degree. The leading coefficient 4 is positive, and so if it's even and positive, it's going to rise left and rise right. My third example, now you'll notice it's not written in standard form, so you have to be careful here. My degree is the largest exponent, so it's a 6th degree, meaning it's going to be even. That means my leading coefficient is -5, so it's a negative leading coefficient. So when you have an even degree and a negative leading coefficient, it's going to fall left and fall right. In number 4, I changed it up a bit. I wrote it as a product of its factors. And so remember, to figure out the degree, you have to add the exponents. So this would be x to the first, so there should be a 1 there. And then plus 2 is 3, and then plus 4 is 7. So this is going to be an odd degree because it's 7th. The leading coefficient will always be what's out in front, so it's +4. So odd and positive would mean that it's falling left and rising to the right. So before we talked about the end behavior, talking about the x-intercepts is what's going on in the middle. So we know when it hits the x-axis, or if it bounces off or crosses the x-axis. So compare and contrast the two ways to write these polynomials. So this one is in standard form. What we like about this is that you can immediately see the degree and the leading coefficient. So this is really helpful with end behavior, but it doesn't tell us where it hits the x-axis. And so then you would have to plug in a value for y and solve for x-intercepts. The other way, the product of factors is really nice because it gives you, if you add the exponents, it gives you the degree, and then this also tells us where the x-intercepts are. So if I use the zero product property, x plus 1 equals 0, that means I have an x-intercept at -1, and then x minus 2 equals 0, I have another x-intercept at 2. So this is telling me what's going on in the middle, but I can also tell what the end behavior is doing. We have something called multiplicity. An odd multiplicity would be exponents that are odd, so to the first, third, fifth, seventh. And anytime you have an odd multiplicity, so an odd exponent, this means the graph is going to cross through that x-intercept or cross the x-axis. So for example, I have x minus 6 times x plus 5 to the third. It has odd multiplicity at -5 and at a +6. So at both of those x-intercepts, it's going to cross the x-axis, not bounce through. An even multiplicity is when you have exponents that are even, so 2, 4, 6. And when you have an even exponent, the graph bounces off the x-axis at that root. So for example, if I have f of x equals x minus 6 squared times x plus 3 to the fourth, I have an x-intercept at a +6. And that's multiplicity is even, so it's going to bounce at a +6, and then x plus 3 to the fourth, that means I have a root at -3, and it's going to bounce off the x-axis at -3. So my first example, it says, without a calculator, write all the zeros of the polynomial, state whether the multiplicity is even or odd, and if it crosses the or bounces off the x-axis. So my first x-intercept, since this is in product of factors form, x plus 3 tells me that my first x-intercept is at -3, It's to the first power, so it has odd multiplicity, and that means my graph is going to cross the x-axis at -3. My second x-intercept, x plus 1 to the third, is going to be a -1, and that's also an odd multiplicity because it's to the third power, and so it's also going to cross the x-axis at -1. And then I have x minus 4 squared. Well, this tells me that my x-intercept, or my root, is a positive 4, and that since the multiplicity is even, because it's squared, that it's going to bounce off the x-axis at 4. So putting those together, you'd also want to look at the end behavior. So this is to the, let's see, first, fourth, this is a 6th degree polynomial, and I have a positive leading coefficient, meaning the graph would go up, or rise left and rise right. It would cross -3, it would cross -1, and then it would bounce off at 4. My second example says when the polynomial is in standard form, you want to look to factor it to find the roots or the zeros, and then state each root and its multiplicity. So out of each term, I could factor out a -x squared, and then I can factor my x squared minus 4x even further to get x minus 2 times x minus 2. And so then I can rewrite that as -x squared times x minus 2 squared. And so this is telling me anytime you have x by itself, that with it's not adding or subtracting a number after it, that means one of the x-intercepts is going to be 0. And so my x-intercepts, or my roots, are at 0 and a positive 2. They both have even multiplicity, meaning it's going to bounce off the x-axis. So looking here, if I were to sketch this, I have a 4th degree and it's negative, so that means my graph is going to fall in both left and to the right, and then it would bounce off at 0 and bounce off at positive 2. Sketching polynomial equations. The first thing you want to do is determine the end behavior. So you want to look at whether the degree is odd or even and whether the leading coefficient is positive or negative. The next thing would be to calculate the x-intercepts and then note whether they cross or they bounce off the x-axis. So that's paying attention to the even or odd multiplicity. Calculate the y-intercept if you can. Calculate and plot one or two more points, and then connect the points to make a polynomial. So remember to make nice smooth curves. Sketching the polynomial, f of x equals x squared times x plus 1 times x minus 4. First of all, its end behavior is 4th degree. So this is to the second. My exponent here is 1. My exponent here is 1. So it's 4th degree. So I know, and then it has a positive leading coefficient, so I know it rises left and rises right. My x-intercepts are at 0, -1, and 4. We call 0 a double root. That's because it has even multiplicity. So that's where it's going to bounce. So it's going to bounce at 0, cross at -1, and cross at 4. My y-intercept, if I plug in 0 for x, is going to be 0. And then another point, if I plug in 1 for x, I get -6. And then I would plot these, and my graph would look like this. So rises left, rises right, crosses at -1, bounces at 0, and crosses again at 4. And then at 1, -6 is another point. Don't worry about how low the graph goes. I will probably tell you what this relative minimum is so that you know how low it goes. But right now, as long as you get the end behavior and the x-intercepts, and if they cross or bounce, that's more important right now than how low the polynomial dips. Writing polynomial equations when given the roots, zeros, or the graph. It says the first thing you want to do is write the roots as a product of its factors, and then next you want to FOIL or use box method to put the polynomial in standard form. So here's my example. It says to write an equation of a polynomial that has the following roots. -2 is a double root. You have 0 and you have 3. So first thing is to write it as a product of its factors. When you have an x-intercept of 0, that means x is going to be by itself. And then I have 3 is x minus 3. And then I told you that a -2 is a double root. So that's going to be a factor of x plus 2, and then it's going to be squared. Next, I'm going to distribute the x only to the first factor. So x times x is x squared. X times -3 is -3x. And then if I FOIL or box my x plus 2 squared, I get x squared plus 4x plus 4. And then last thing would be to use box method to put it into standard form. And this video covered section 2.3, polynomial functions.